First, let's start off with a mini lesson on bonding. There are three different bonds: ionic, polar covalent, and nonpolar covalent. Ionic bonds are formed between a metal and a nonmetal. On the periodic table of elements, all elements to the left of the staircase are metals, and all elements to the right of the staircase are nonmetals. The elements on the staircase B, Si, Ge, As, Sb, and Te are metalloids. Covalent bonds are formed between two nonmetals. Whether the bond is ionic, polar covalent, or nonpolar covalent is dependent on the electronegativity difference. The electronegativity of each element can be found on table S. If the electronegativity difference is equal to or greater than 1.7, the bond is ionic. If the electronegativity difference is less than 0.4, the bond is nonpolar covalent. If the electronegativity difference is between 0.4 to 1.7, the bond is polar covalent. In nonpolar bonds, electrons are shared equally, symmetrically. In polar bonds, electrons are shared unequally, asymmetrically. Using the crisscross rule allows you to cross over the charge of the ion in order to determine the ratio of the ions. It can only be used for ionic compounds. The elements should be aligned and the symbol for the element should be brought down. The charges should cross over and coincide with the opposite element. If necessary, the formula should be simplified. In the example shown, Pb has a charge of +4 and O has a charge of -2. Pb and O will be brought down, but the charges will be crossed over and will signify the amount of the element in the compound. There will be 2 elements of Pb and 4 elements of oxygen, but this should be simplified, and 2 should be divided by 2 to make 1, and 4 should be divided by 2 to make 2 to get the empirical formula. Drawing the structural formula. When you draw the structural formula, you need to take into account how many valence electrons each element has and how many elements are in the compound. Each element has to be surrounded by 8 electrons to complete its outer shell. The only exception is hydrogen, which needs 2. In this example, let's draw the structural formula for H2O. H has 1 valence electron, but since there are 2 H elements, that will be 2 valence electrons. O has 6 valence electrons. This means there will be a total of 8 valence electrons. When drawing, there should be a bond between each of the H atoms and O. Each bond is 2 electrons, so H minus 4 is 4 electrons left. These leftover 4 electrons will be used to complete oxygen's outer shell. Hydrogen already has a complete outer shell because it only needs 2 electrons to complete its outer shell. We are now going to complete a worksheet that can be linked in the description below. Determine whether the bond is an ionic or covalent bond. NaCl is an example of an ionic bond between a metal and a nonmetal. NO is an example of a covalent bond because it is between 2 nonmetals. The electronegativity value of N is 3, and the electronegativity value of O is 3.4. 3.4 minus 3 equals 0.4, which means it is a polar covalent bond. CH4 is an example of a covalent bond because it is between 2 nonmetals. The electronegativity value of C is 2.6, and the electronegativity value of hydrogen is 2.2. 2.6 minus 2.2 equals 0.4, which means it is a polar covalent bond. LiF is an example of an ionic bond between a metal and a nonmetal. CO2 is an example of a covalent bond because it is between 2 nonmetals. The electronegativity value of C is 2.6, and the electronegativity value of O is 3.4. 3.4 minus 2.6 equals 0.8, which means it is a polar covalent bond. However, CO2 is special because it has a structural formula is symmetrical. This makes the molecule nonpolar covalent. H2O is an example of a covalent bond because it is between 2 nonmetals. The electronegativity value of H is 2.2, and the electronegativity value of O is 3.4. 3.4 minus 2.2 equals 1.4. This makes the molecule polar covalent. Use the crisscross rule below. When using the crisscross rule, you can rewrite it, so we have K plus and Cl minus. Then you should bring down the symbols and exchange the signs. We have KCl. Now we have K plus and Cl minus 5. Bring down the elements. K will become 5K and Cl will still only have 1. Our next problem is Rb plus and F minus. Bring down Rb and F but exchange the charges. We still have RBF. Now we have Mg plus 2 and Cl minus. Bring down Mg and Cl but exchange the charges. So it's MgCl2. Now we have Mg plus 2 and O minus 2. Bring down the Mg and the O, but exchange the charges. So it's Mg2O2, but this can be simplified to MgO. Now we have Mg plus 2 and OH minus. It's important that the OH stays in parentheses because that's the way it was given. Bring down the Mg and the OH, but exchange the charges. So it's MgOH2. Model each molecule's structural formula. When drawing HCl structural formula, remember that H needs 2 electrons to complete its outer shell. H has 1 valence electron and Cl has 7 valence electrons. 1 plus 7 equals 8. After drawing a bond between H and Cl, there will be 6 electrons left over. These 6 electrons will complete Cl's outer shell. S has 6 electrons in its outer shell, and oxygen also has 6 electrons in its outer shell. For oxygen, 2 times 6 equals 12, and 12 plus 6 equals 18. After drawing 2 bonds between the 2 elements of oxygen and sulfur, 14 electrons will be left over. But with only 14 electrons, the outer shell of each atom cannot be completed, so another 2 bonds should be drawn. Now sulfur's outer shell is complete, and 10 electrons are left over. 8 electrons will be used to complete both oxygen's outer shell. The last 2 will be added to sulfur. This is a unique scenario where sulfur has 10 valence electrons. This creates a dipole as the electrons are most attracted to sulfur, creating a bent shape. N has 5 valence electrons. 5 times 2 equals 10. After placing a bond between the 2 atoms of nitrogen, 8 electrons will be left. This is not enough to fill both nitrogen's outer shell, so another bond will be added between them. This will leave 6 electrons left over, and this is still not enough to complete the outer shells. After placing a third bond between them, 4 electrons are left over. Each nitrogen will receive 2 more electrons to complete its outer shell. Nitrogen has 5 valence electrons, and H has 1 valence electron. 1 times 3 equals 3, and 3 plus 5 equals 8. After placing 3 bonds between the 3 hydrogens of nitrogen, each hydrogen will have its outer shell completed, and there will be 2 electrons left over. These 2 electrons will complete nitrogen's valence shell. For BaCl2, Ba has 2 valence electrons and Cl has 7 valence electrons. 7 times 2 equals 14, and 14 plus 2 equals 16. After drawing 2 bonds between the Cl atoms in Ba, 12 electrons will be over. This will not be enough to complete all of their outer shells. Another 2 bonds will be added between the 2 atoms of Cl and Ba. 8 electrons will be left over, and barium will have a complete outer shell. Each chlorine atom will have 4 electrons added to complete its outer shell. C has 4 valence electrons and H has 1 valence electron. 1 times 4 equals 4, and 4 plus 4 equals 8. After drawing 3 bonds between each hydrogen atom and carbon, 2 electrons will be left, and each hydrogen will have a complete outer shell. The last two electrons will be used to complete carbon's outer shell.